In this video, we're going to be talking about fitted values and residual diagnostics. And these are very important things to do when you're trying to produce any type of forecasts. When we talk about fitted values, these are values that are obtained when we use the estimated model parameters on our training data set. Okay, so in other words, with fitted values, we're trying to see how well does the model fit the data. Okay, we're not talking about forecasts yet, but we are talking about fitted values. So this is very similar to the y hat you obtain in your multiple regression analysis, for instance, and see the fit of the model. Now, the fitted values are usually compared to the training data that we have because we're not yet producing forecasts. So sometimes we try to drop the subscript when we talk about fitted values. Usually fitted values are written as y hat t, what is y hat at time t given all the available information at t minus 1. Whenever we say y hat t, we are referring to fitted values and not the forecast in any way. Okay, so these are, even though they look like, when you write something like this, even though this looks like you're trying to produce a forecast, these are often not true forecasts because these parameters are based on all the data that you have in your training data set. So fitted values, in other words, are always one step ahead forecasts. Okay, one step ahead meaning that if we are at t minus 1, at period t minus 1, and we have all the information on y up till t minus 1, we are trying to estimate what is y in period t. So the fitted value is always going to embody the information in or until t minus 1. So in that way, it is a one step ahead forecast. And you'll be able to see this better when we try to talk about a graph. So that brings us to, if we know what the fitted values are, we can then try to assess what our residuals look like. And the residuals are usually the difference, or are calculated as the difference between the observed value, which is something from your training data set, a value from your training data set, and its fitted value. So residuals at time t, represented by et equal y at time t minus the fitted value at time t based on the information at t minus 1. Now there are some assumptions that we that make our residuals well behaved. So one assumption is that residuals should be uncorrelated. If they aren't, then our model is not taking into account all of the information that is in our data. Okay, so there's some information that's left in residuals that can be exploited to compute those fitted values. Okay. The second assumption is that the residuals should have a mean equal to 0. If they don't have that, then forecasts are considered to be biased, or fitted values in this case are considered to be biased. So since we know what white noise processes are, we want our residuals to display properties of a white noise process. We don't want that there should be any type of patterns that could be exploited in our residuals. Of course, we want a lot of patterns to exist in our original data set, but not in the residuals. So we've talked about prediction intervals in the previous video, and two additional properties that could be useful for computing prediction intervals are that the residual should have constant variance. Okay, so they should, constant variance would mean that you're not seeing a period where the residuals are displaying very low variability and then a period where the residuals are displaying very high variability. So overall, if you try to look at these fitted values, they should look like they are displaying some constant stable variance. And lastly, that these residuals are normally distributed. There are many nice properties of normal distributions that can be used to produce prediction intervals. But this is not always the case when we deal with financial data, for instance. Now, in this example, you're familiar with this, so I won't go over this code. But here we're basically looking at the Google stock price in 2015 using the GAF_stock dataset. Okay, and we're updating the symbol here. Now here's a plot of that data set, and you can see that there's really no set pattern here. There's no underlying trend that we can see except for the more recent years, or the more recent values here. And then we see some outlying observations here, and then maybe even here. Okay, where there's like this stock price is climbing up, okay, with some troughs, small troughs over here. So a naive forecast in this case would tell us that the fitted values, the value of yt given information at t-1 just equals the previous period's value of y, which is yt-1. So the error can be, the residuals can be written as yt minus yt-1. Okay. So residuals are one-step forecast residuals in this case. Okay. So when we fit a model to the Google data, we can do so by looking at a naive model on the closing prices. Okay, so this you're familiar with, how to do this. The function that we use to obtain fitted values and residuals is called the augment function. Okay, so if you use that augment function on your fitted data, okay, you're going to get a symbol in the end. That symbol is going to have different columns that are going to give you different sets of information. So the first column is going to display your model. Okay, so we know that we only had put in one model here, which was naive, so this says naive. And in the last two columns, you're able to see the fitted values of the series. So obviously for the first period, it isn't defined, but for the rest of the periods, it is defined. Okay, the residuals are given in the last column. Okay, so maybe it's a good idea to try to take a look at what does that look like on a graph. So here what we're doing is taking the fitted values and plotting them. Okay, so we'll use ggplot, and for our x-axis we're going to have the number of trading days, so x equals trading days, and then we are going to have different, at least two different values of y. So one value would be the original price, which is y equals the closing prices, and the second line that we want to superimpose on this is the fitted value of the series. Okay, so here we see that the red line in the graph is the data set, the original data set, and the fitted value is the green line. Okay, now if you notice carefully, it looks like it's moving together, right? The fitted values are moving together with the data, but the fitted values just seem like they are one step ahead of the data. Okay, And this is not surprising based on how fitted values are defined. Fitted values take the information until time t minus 1 and produce a forecast for the next period. Okay, and the forecast for the next period is just the previous days, or yeah, previous days in this case, previous days value. Now we can try to take a look at our residuals, and one way to do that is just use the augment command on the fitted data and auto plot the last column, which is dot resid, which contains our residuals. And so here we see that our residuals seem to be centered around 0, right? You look at the y-axis here, and you look at these trading days, and then you have these these unexpected price jumps or price declines that were happening in our data that lead to these large residuals for some of the trading days. But overall, we are seeing that residuals are just 0. We can also take a look at a histogram. So you are familiar with the histogram command. When you look at the when we're working with the ggplot package, we can let R create bins for us, or we can give the number of bins in this case. So we're just looking at how many values, right? On the y-axis, we have frequency, right? How many values are centered around 0. So it seems like most of the values of our residuals are centered around 0. There are some outlying observations here, outlying residuals here, where there are some large values here. Very few though, right? The ones we were seeing, very few in that graph that are large. So if we look back at the properties that we want our errors to be normally distributed. A normal distribution would look like this. But in this case, we're seeing that there is a long right tail that tells us that even though the mean of the residuals is 0, the distribution itself is not normal. And this is very particular of financial data. We can take a look at if there is any correlation present in our residuals. So are the residuals at time t correlated with residuals at time t minus 1 or t minus 2? And you can look at it for so many lags, right? So on your x-axis here, you have lags. This is your autocorrelation function of residuals. Remember, we don't want any type of pattern to exist in our residuals. So most of the times we want that the residuals should display autocorrelations that are not significantly different than 0. So that means that all of these bars should always stay inside the Bartlett bands that you see here. So we're basically using the ACF function to plot the autocorrelations of our residuals. Barring one lag at lag 17, most autocorrelations are insignificant, right? That means they're not significantly different from 0, which is good news for us. We want this to happen. But we don't want this to happen with our data. We want our data to always display autocorrelations that are significantly different than 0. But for residuals, we want this to happen. So we assume that the residuals are white noise. That means they're uncorrelated, they have mean equal to 0, and they have some kind of a constant variance. If they aren't, then there is some information left in the residuals that should be used in computing forecasts or fitted values in this case. So typically we want to check the residual diagnostics in these ways to see what is going on with the ACF, etc. Okay, but we want them to look like white noise. So how can we test for this? So one way is to just look at these, but the other way is to use some kind of a sophisticated test. So This type of test, there are two types that we'll talk about, two types of tests. One is called a box Pierce test, and the other one is called the Leung box test. And they are types of Portmanteau tests that consider a whole set of autocorrelation values to see if that entire set is significantly different from a zero set. Okay, so portmanteau is a French word for a suitcase containing a large number of items. In this case, the large number of items are the autocorrelations for different lags. So we want to see if that entire set together is different than the zero set. The box Pierce test uses a Q statistic, which is defined as follows. The Q statistic equals the length of the time series t times the square of the autocorrelations, where k goes from 1 to whatever the lag is. H is lag in this case, it's not the forecast horizon. Okay, so this is the maximum lag that's being considered for autocorrelations. Now, whenever we are doing a statistical test, what we want to do is set up our null and alternative hypothesis. So our null hypothesis in this case is that RK, which is autocorrelations, representing autocorrelations, are equal to 0. Okay, and the alternative hypothesis is that these autocorrelations are not equal to 0. Now, what we want is this first thing here, this null hypothesis, to not be rejected. Okay, so whenever you can look at Q values or you can look at P values. I prefer P values because they're easy to interpret. If the P values are very large, right, then that would indicate that we fail to reject the null hypothesis. If we fail to reject the null hypothesis, then we would say that RK is 0. So each RK is 0, okay, where K is just representing the lags, okay. And if the p-value is very small, that's bad news for us, okay? Because if p-values are small, then we would say that we reject the null hypothesis that RK is 0. That means RK is not 0, right? If p-values are small, this is telling us that we're leaning towards autocorrelations not being equal to 0, okay? So this is how we would conduct this test, and we would interpret p-values. The test isn't really good for large values of lags. So the book says the maximum lag that you can put in when you look at the arguments is t divided by 5. Okay. The second type of Portmanteau test is called the Leung box test, which is a more accurate measure of whether autocorrelations are significantly different from a zero set. And this usually performs better if your sample size is small. Now, I'm hoping that that's never the case if you did a project or not, but sometimes you can't help it and you are given smaller sets, sample sizes, okay? But this is just more accurate. Okay, again, it's just a different version of the box Pierce statistic. Now, how do we do this in R? One thing we want to remember is that if data are white noise, then the Q statistic has a chi-square distribution with h minus k degrees of freedom. So h is the max lags, and k is the number of parameters. So this is capital K. K is the number of parameters in the model. Now, the way we write the code in R is that we wrap the box.test function around the residuals, and then we test the residuals. So in this case, we're saying box.test is wrapped around augment fit, and we are extracting residuals, which is the last column. that we would get if we just had augment on fit. And we are going to look at 10 lags. So H is 10 here. This is the max lag. And since this was a naive model, we haven't really lost any degrees of freedom. Okay. And so that's equal to 0. And the type we are looking at is Lume box. Okay. If you just look at the type, you can change this argument to looking at a box Pierce set. Okay. And now we can try to look at what the output is. That's what more important. And the p-value is large. Okay. Which is to say that we fail to reject the null hypothesis, which is good news for us, because rk equals 0 means if we fail to reject this null hypothesis, this means that our residuals are white noise. Now, if you wanted to do all of this, all of these nice graphics together in one command, you can take the augment fit, you can use the pipe function, and you can use the command gg_tsDisplay on the residuals. Okay, so you want to wrap this around the residuals, and you can say plot equals histogram. So this is going to give you that histogram of your residuals. You can do many more things. Again, you see the residuals, the plot of the residuals. You see those outlying residuals 1, 2, and 3. And then you can also see the autocorrelation functions, and you can also see whether this is a normal distribution or not. So you can try this on your own. You can pause the video here and try this